So in this video, I'm just going to finish off the proof that I started in the previous video, and then I'm going to continue with multiple slits. So in the previous video, we equated these two sides of this equation, n lambda, which is the number or like an integer number, and wavelength, equals d sine theta. And this side we derived from this triangle here, which gives you the path difference. So in effect, we're calculating path difference two different ways to give us n lambda equals d sine theta. Now, destructive interference is the minima. So this section here, we could actually come up with an expression for destructive interference using exactly the same idea, but the only thing that changes is that the path difference would not be equal to a wavelength. It would be equal to half a wavelength in order to account for the fact that when a crest leaves here, it will meet a trough, which is half a wavelength away. And so the path difference would have to be equal to some whole number times half the wavelength. So just bear that in mind. It's not commonly referred to when we're dealing with two or multiple slits, but sometimes there would be a reference to it. So remember that it would be n plus a half to change this equation to refer to, instead of constructive, to refer to destructive interference. I hope that makes sense. If not, we can talk about it when I come back. Okay, so now let's get back to this equation from grade 11, which relates not to the angle theta, but talks about this ratio of S over D. Now, the reason why we can use this equation here, S equals lambda D over D, is actually the same equation as this. But we're making we're using this assumption based on the fact that the angle theta is basically the angle from the horizontal, from the zero order maxima to the first order maximum. Now this distance is S, right? And this distance is D. So the assumption that we're playing with is that D, being way bigger than S, right, means that this angle is very small. And so for very, very small angles, sine theta is actually equal to theta. And tan theta is equal to theta. So I know it sounds like a bit of a stretch, but it does make sense. If this is very small, then sine theta equals tan theta, which is equal to theta, which is also equal, because tan theta is equal to S over D, and so tan theta is equal to S over D, which is equal to theta. And so you can replace sine theta, you can replace this sine theta with S over D. S over D. And so your equation can equal lambda equals D S over D, which is the way that we apply this equation in topic 4. Okay, so I think that's everything. I think you've got everything you need to be able to answer the assignments. So you can stop the video here and finish that assignment. And in the next part of the video, I'll talk about multiple slits. Now, multiple slits and diffraction gratings are a variation of what we've done with double slits. And this is an example of a multiple slit and diffraction grating interference pattern. You can see that the interference patterns are really similar. They seem to occur in the same place. They just happen to be much thinner. This is what happens with two slits. You get this quite thick band, and it gets thinner and thinner. And it also becomes clearer, right? So you find that all that energy is no longer spread over such a wide area. As the number of slits increases, the intensity seems to increase and be less spread out. This is an important pattern, and you have to be quite clear with it and understand it. Now, what's a diffraction grating? Diffraction grating just happens to be a filter which has loads of slits, to the point where you might have maybe 300 lines per millimeter, right? Now, the relationship that you would need to use is the same as before, because the proof is the same. It just happens to involve more gaps. N is a whole integer, lambda is the wavelength, d is the distance between gaps, and sine theta is the angle between the zero order and the first order, or the order in question, right? Now, the only thing that changes when you're using a diffraction grating or a multiple slit is you have to calculate your d in a slightly different way. If you were given the amount of gaps per millimeter, like this one, 300 lines per millimeter, you would say divide 1 millimeter by 300 to give you that distance, which would be very small. The rest of the calculations are very, very similar. Now, qualitatively, there is a little bit more explaining to do, which we've kind of come across already. I explained in a few seconds ago, or a few minutes ago. With two slits, you get thick bands which are equidistant. As the number of slits increases, the relative position of this, the bright fringes stays the same. However, the thickness of the bright fringes becomes much thinner as the number of slits increases, and so you get the energy spread over a much smaller area, but it is more intense. If we were to look at the graph, let's have a look at a graph of intensity against distance, you would find that you have a greater intensity to your peak, but the distance it covers is much smaller. So this would be a large number of gaps or slits, which is, for example, a pattern due to diffraction grating, and this one would be your two slits, much wider and lower in intensity. Okay, I think that's it. There's one thing I forgot to do in the previous section, which was explain this distance here, what was on the x-axis. Normally, when you have intensity and distance graphs, you would have a number, right? In this particular graph, they're expressing it as lambda over d, or sine theta, right? You can see this is on the x-axis. Now, this comes from this equation. So the position on the x-axis, because it relates to sine theta, if you arrange this equation, it would be m lambda over d. And so the n lambda over d is equal to sine theta. And so on this graph, it's expressed on the x-axis, sine theta would be equal to lambda over d, or 2 lambda over d, etc. So it's just another way of writing that angle. Okay, it is sometimes expressed like this, though once again I repeat, it's usually a specific position, a distance. And I think that's it. This should be enough to keep you guys going for a double lesson, and then I will just wrap this up on Monday and we'll talk about single slit interference.